Recording in progress.
Okay, good morning, everybody. Welcome to our weekly seminar. Today we have the pleasure of welcoming Dr. Arturo Leon from Florida International University. He's an associate professor of water resources engineering. Dr. Leon's research areas involve multi-phase flows, resilient flood control, computational fluid dynamics, and physical modeling of hydraulic structures. So today, Dr. Leon is going to speak to us about overflows in combined sewer systems. So I'll turn it over to you, Arturo.
Thank you, Dr. Chin, for the invitation, first of all. And I apologize for the noise. There is a construction, so I'm sorry about that. I think it's going to go in the next few minutes, so it should be okay. So today I will talk about minimizing overflows in combined sewer systems, and I will show you some examples about this. Let's see. Okay. So first, I would like to acknowledge my students. As you guys know, the students do all the work. So several students have worked on this project over the last 5-10 years. And also we got grants from EPA, NSF, and other agencies for this work. So today I will talk about, the outline is as follows. First, I will talk about an overview of sewers. What are sewers? And also I will talk about geysers, because geysers is a big problem in sewer systems. I will provide some laboratory tests we have done in the past, some numerical simulations from 1D to 3D. And then I will finalize talking about an artificial intelligence algorithms for the prediction and the mitigation of combined sewer overflows. So what is a combined sewer system? A combined sewer system is a system that combines in the same pipe storm water from the rain plus the sewage. So in the same pipe, they convey wastewater plus storm water. That is a combined sewer system. Okay, and as you can see here, we have houses. Basically, all the sewage goes to some connectors, secondary connectors, and finally they go to a deep tunnel. Okay, so let's see. Okay, so this is a kind of one picture of a tunnel. These deep tunnels are huge. The diameter can be up to 10 meters, or 30 feet, or even 40 feet in some cities in the US. So they are huge, huge tunnels. So why do we need to study this? In the US, more than 800 cities operate one or more combined sewer systems. So there is a lot, especially the old cities, Chicago, New York, some places in California, Minnesota. They have many of those cities have operate one or more combined sewer systems. Okay, and several combined sewer systems are not operated at full capacity, because they want to prevent undesirable phenomena. Example, geysers in storm sewer systems. So if we operate combined sewer systems at full capacity, we can reduce combined sewer overflows, right? Because we are maximizing the storage, and therefore we are reducing the release of sewer overflows. So there is geysers events all over the world. The US, China, Canada, Europe, everywhere. I asked my students to kind of go to YouTube and get some of the videos in the US. And he found some states, some examples. Let me show you one example. This is a geyser in Chicago. This is another geyser in New York. So these are kind of relatively frequent events that happen all over the world. Can you guys hear me well?
Yeah, we can hear you.
Okay, great. This is a Stormsewer Geyser in Minnesota, in the Highway I-35. This is, I think, in 1999, so about 22 years ago, 23 years ago. So these are kind of interesting phenomena that I was attracted when I came to the US to study my PhD. And so very complex phenomena, very interesting, not well understood, very complex as well. And then, so to maximize the efficiency of a combined sewer system, if we want to minimize sewer overflows, of course, we have to do a number of experiments to understand how the system is working. This is an experiment example of a vortex flow restrictor to kind of to check how much water is going to the sewer system. So we have to basically simulate well the conditions in the sewer system. These are some experiments for geysers that we have conducted before. This is a facility we have at FIU. This is a kind of an old video, but we have a facility to do simulations. And then we have to measure a number of parameters. And one parameter that is extremely important in this case is measuring the void fraction, which means how much air is in the system in real time, right? So this is we use a wire mesh sensors to basically quantify how much air is in each mesh in the at various locations in the piping system. These are some videos of geyser experiments we have performed. So they are very violent events. They are very violent events. The heights might go over 100 feet, and we have done this in the lab while I was at Oregon State. When I was before there, we have done some experiments, and right now we are conducting some experiments at FIU. So this is in a slow motion, the geyser at a quarter speed. So this is a kind of a consecutive eruptions, similar to what you observed in the field. So these are very dynamic events. We get data to understand what's going on in those geysers, and then of course we can propose some retrofitting approaches to minimize those events. And one easy way to mitigate sewer events is by reducing the amount of air that goes into the vertical shaft, which is called also drop shaft. So we have tested those, and then by reducing the inlet, we can reduce the geyser. We can reduce the geyser height. These are some data we have done. Not doing anything, reducing the inlet by half, by 1/4, and by 1/8. You can see that the geyser height, which is on the left, this is the HG dimensionalized with a diameter. You guys can see that the geyser height will be substantially reduced by limiting the amount of air going into the drop shaft. Of course, we have to do also numerical modeling to give us a better perspective of what's going on. We have used the open source model, in which we change the algorithm sometimes. We have used the classical volume of fluid method. We have performed 2D and 3D simulations for this. This is just a mesh of a drop shaft, you can see. And basically what's going on is, this is a video that shows that you have whenever it rains, there is an entrapment of air. That air starts to travel slowly. And then once it finds the drop shaft, that air is released. And under some conditions, those might produce violent geyser eruptions. Okay. This is another simulation Here again, we have the air approaching slowly to the drop shaft. And then in this case, the drop shaft is kind of a very tall. I mean, the height is much higher than the initial water depth. There is initial mixing. That initial mixing basically reduces the density of the mix, right? And then, but the pressure in the tunnel is the same. It doesn't change. So the difference, the gradient of pressure will cause these eruptions because the density of the mixture in the drop shaft is relatively, is reducing. And then at some point, there is going to be a threshold where these geysers will occur. This is a simulation of the combined sewer system in of the Calumet system in Chicago. This is, as you can see here, I don't know if you can see here on the circle, the gate is opening. So if we want to minimize sewer overflows, we have to control. We have to know what to do with the gates. We have to basically operate those gates to minimize sewer overflows, right? The idea is to maximize the utilization of the combined sewer system. And then we have to simulate those things. This is a model called the Illinois Transit Model, which I developed, I think about 10 years ago. This is used for simulating combined sewer systems in various places in the US and also around the world. So this model is intended for modeling the dynamics of very complex systems, including the operation of gates, pumps, and so on. This is another simulation. This is so you might have also transients, and you might have extreme dynamics. You might have multiple shocks, multiple interactions, air-water dynamics in the sewer system. So we have to be able to more or less represent this in the model. Also, the optimization involves fixing some problems in the combined sewer system. This is the simulation of the pumping station in the 27th Street in Chicago. So this system had a problem because whenever there was a lot of rain, there was a backflow. So the water wouldn't go into the deep tunnel, but instead there was a backflow, and it would basically flood the pumping stations. And this was due to a number of reasons. One reason was that the drop shaft, which is this, didn't have enough capacity. So we found that using the three-dimensional numerical model, we found that didn't have enough capacity at the beginning. So there was a backflow. And then once they fix this, we find out also that the gates, let's see if I can, let's see. Then after there was some expansion of the drop shaft, there was no more problems. However, oops, what happened here? Let me see if I can go back. Okay. You guys still see my screen?
Yeah, we can see it.
Okay, great. So another problem was regarding the weight of the gates. So there was some tight gates. Let me see if I can play again. So initially they were made of iron. They were very heavy. So whenever there was a lot of water coming from upstream, the water was not, the momentum of the water was not enough to lift the gates. So there was a backflow as well. And then we recommended to change those gates to kind of make more lighter. And then with that, also there was the problem was fixed. This is in the access to the main shaft. So involving maximizing the operation of the combined sewer overflow involves many steps. Okay, so also, and this is again the Chicago River. Also, whenever you have a combined sewer overflow, you need to decide when is the best time. I mean, if you are going to release wastewater to the river, you need to know when is the best time to release wastewater, because the conditions are not the same during the morning, are not the same during the afternoon, during the evening. There are some biological and chemical processes that are happening there. And also because depending on the rain, the water levels might be high or might be low. And under those conditions, there might be problems. For example, there might be flooding to some areas in the around the river system. So we need to know when is the best time to release sewer overflows if we have to. Okay, so now I will talk about artificial intelligence for prediction of sewer overflows and the mitigation. This was prepared by my current student, one of my current students working in sewer overflows. So we have applied this. We have made this application for the Puritan-Fenkel sewer system in Detroit, Michigan. This is probably the biggest combined sewer system facility in Detroit. We are doing these applications to right now to 2 more applications, but we are not completed yet. But this is kind of a more or less close to be completed. So as you can see here, we have the catchment, the links. It's not that clear, some of those elements, but we have a manholes, outfall, storage units, control units. And this is a relatively, this is from the 4 we have, this is the most simple system. Even though it's very complex, but this is the most simple of all the 4. So the idea is to use physics-based deep learning models. So the idea is to basically combine the machine learning model using true physics-based modeling. In this case, we use the SWMM model, which is a stormwater management model of EPA as our simulation model, and also we use field data provided by multiple municipalities. This is in this case it's Michigan, and we have data from Minnesota, from Ohio, and we are working with several consultants and several municipalities. And the SWMM model requires data of rainfall, the conditions of downstream, how the combined sewer system hydraulic structures are operated, the pumping stations, and so on. And then after we develop the deep learning model, which is typically, after we train the deep learning model, we will only need the rainfall and the outfall conditions to basically predict the water surface, the flow rates, and the sewer overflows. So we have used, as I mentioned before, for the simulation, we have used the SWMM model. And then we have used multiple machine learning models. Example, we have started with a multi-layer perceptron model, which is basically a feed-forward artificial neural network model. So basically what happens here is we have an input layer, okay, and we have an output layer, and between we have a hidden layers. But all the process is feed-forward. So basically, this is the kind of a type of well-known machine learning models. And then we also have used the, let's see if I can, okay. Then we have used also the recurrent neural network model. In this case, some connections between the nodes are allowed. So we can create some loops or some cycles. So this is this does a little better job than the previous one. This is kind of the link. So we can, we can create some loops in this neural network model, and those loops also can be based on some questions. If you have this, do that. So there are some rules that you can follow to create this. And then we have the gated recurrent units. In this case, we can specify threshold values. So we can say, okay, if you arrive this, if you get this value, do this, do that, or so they are called basically what we have here. We have a reset gate, current memory gate, or final memory gate. So basically, they are kind of a conditions. If you achieve this, either delete this value or do this or do that. So it's a kind of a gate. So it's called gated recurrent units. And let's see here. Okay. And then we have the long short-term memory, LSTM, and this model allows a feedback, which means allows a cycle with 3 gates. So you can forget the information input gate and output gate. So if a condition is reached, you can do some things, but also allows a feedback. This is and then we have convolutional neural network models, and this is some of the models we have played, but of course there are many more. There is attention-based models. This is kind of one of the models that is kind of having more application recently, especially this model called transformer model, which is being used widely in the last few years. In the case of the sequence-to-sequence model, basically the previous output. So the previous output is used as the input, right? So basically, all the processing is made in sequence. For the case of the transformer model, it's possible to add weights differentially, and then basically for various components of the input data. This is a kind of also, I mean, this is being used a lot recently. Okay, I'm not sure what is going on. Okay, let me see if I can. Oh, now it's going. Okay, so this is based on the simulations we have done. We have created outputs with all of them. Pretty much all of them do a good job, especially the transformer and the recurrent neural network. So this is the results for the recurrent neural network. So we have compared, in this case, we have the water depths at multiple nodes using the SWMM model and using the recurrent neural network model. As you can see here, the prediction by this recurrent neural network model is very good. It's very, very good. We were very surprised with this, and we got very good results, which basically match the results of the model SWMM, which is the simulation model. Here again, we have this is the comparison of the duration of the overflows, the starting time of the overflows. And we can see that the results are very, very good. So we have the example here. You can see let's see if I can draw something here. You can see here, example, the duration of the overflows with the machine learning model and the SWMM. They're pretty much the same. In some cases, there are some discrepancies, but they are very minor. The starting time of the overflows are also, they are basically between 1 to 3 minutes difference for when the overflow is going to start. So I think in overall, considering the uncertainty of Stormsewer systems, I would say that the result that the machine learning model gives is good enough for practical purposes. Okay, let me see if I can. Okay. Okay. So let's see. Okay. So now one of the applications of this is to be able to optimize or basically minimize sewer overflows. To minimize sewer overflows, we have to use some kind of optimization for the optimal control. Prediction is relatively easy because in prediction you have a set of conditions and you want to predict what's going to happen. But now we want to optimize. Now we want to find out how we should move the gates up and down during time. Example, if the rain is going to be during one day, we want to know how we should operate the gates before and after the rain, so we can minimize sewer overflows. So, and if you use the classical optimization, example, genetic algorithms or pattern search or some kind of nonlinear solvers, those methods are very time consuming. I have done this before. It might take one day to come up with a solution. So, however, for practical purposes, you need to get a solution basically in real time. So we have used the concept of reinforcement learning. And reinforcement learning is used for board games, self-driving vehicles, robots control, and so on. So we have used this concept of reinforcement learning applied to sewer overflows. So basically, in the reinforcement learning, we construct one or several neural networks to maximize some kind of reward, some kind of objective. Okay, and we have used again to develop this model as a simulation. We have used the SWMM model as well. And the reward function to maximize is to minimize. I mean, maximization is a negative of minimization, right? So in this case, we want to minimize the overflows coming out of the sewer system. So again, we have tested multiple algorithms for the reinforcement learning, and then for application, we found that this model is the best, giving better results. We are still testing, but this is so far what we have found in our application. So we have done some comparisons of overflow at several nodes. It's not too clear here, but we found that using the reinforcement learning, so we have compared the do nothing approach with the optimal control, and we found that the overflow can be substantially reduced. Sometimes, for some conditions, you don't have any sewer overflow if you operate the conditions. If you operate the gates according to some rules provided by the reinforcement learning, but if you do nothing, in most of those cases you will have a sewer overflow. So we were very happy actually with these results, and this is for one application. What should be the optimal gate positions to minimize sewer overflow? This is in 7 locations. So this sewer system has gates at 7 locations, and we, as you can see here in the bottom, let's see, as you can see here, this is a rain that happened over a period of about 3 days, and then we found what should be the opening of the gates during those 5 days. Oh, sorry, during those 3 days. Every 10 minutes, and then according to those, we were able to reduce sewer overflow. This is a preliminary result, but we are in that process right now. But according to this, the overflows in some cases were reduced completely, and in some cases the overflows were reduced by 30%, 50%, and so on. The CPU time. the CPU time to find these optimal gate positions for this system was 3 minutes. So if we have the prediction of rain, and if we have the boundary conditions in the sewer system, so we know what are the levels of the outfalls, and all of those conditions, we can come up with what should be the optimal gate positions every 10 minutes for the whole rain. So 1 day before the rain and 1 day after the rain during 3 minutes. In 3 minutes, we can get the solution using the machine learning approach. Okay, so I think I went a little bit fast with the intention that there is some questions. So I hope to entertain some questions. Thank you so much. Let's see if I can. Okay, see if I can.
Okay, thank you very much. While everybody is thinking of their questions, I just have one question with when you compared the machine learning results with the SWMM results, did you have any actual measurements to compare, let's say, the SWMM results with?
Yes. So first, the SWMM model is validated and calibrated using actual measurements in the system. So that's one thing. So we use dry flows and wet flows for validating the SWMM model. So that's one thing. And second, the cities, they have actual data. So we can use that for prediction and validation. So actually, we are in the process now. Right now, what we are trying to do is we are trying to simulate some historical overflows.
Mm-hmm.
So we can compare when the overflows happen and if that matches with the model. So we're in the process of that right now.
Yeah, I mean, the only thought I had there was perhaps there could have been an improvement in the SWMM model. So then if you compare the machine learning with the actual data, it might actually perform better than SWMM when compared with the actual data.
Yes, the only issue here is we have to use some kind of simulation model because the data acquired is very limited. There is only data at some locations and everything. However, the SWMM can provide us a better picture of what's going on in the entire sewer system because the sewer system is very complex. It has in this case, it has 7 miles of deep tunnels and connectors and so on.
Yeah. Okay. Does anybody in the audience have any questions? No, I don't hear it. So it seems like everything was perfectly clear to everybody. I have one more. What is the future of combined sewers? Do you see new ones being constructed, or are you just sort of working on the operation of existing ones?
Yeah, that's a very interesting question because this is a question that many people ask me. And also I went to several conferences and several seminars with municipalities, and some people are in favor of keeping combined sewer systems. And some people, they say that the sewer systems are not a good investment. They are not smart, and then eventually they will disappear. I mean, it's kind of hard to think that they will disappear because it would cost many trillions of dollars to replace the sewer systems because we have 800 cities having investments in sewer systems. So replacing them, yeah, it could be done, but it will take a century or so to replace this system. In particular, I think that it's going to continue for a while, but I think many cities, example, Florida doesn't have many combined sewer systems. Florida is kind of have a separate sewer system. So I believe that in the future, I mean, it's my personal opinion, I believe that combined sewer system might disappear, but it will take a long, long time.
I see. Okay, Gong, I'm going to, why don't you ask your question yourself, Gong?
Hello,
Okay, I
Dr. Chen,
will,
can you hear me?
Yeah, go ahead, Gong.
Sorry,
Go ahead with your
there's
question.
another student talking in my office. So, so I was, my question is about, do you need to consider whether your machine learning model may have or may not have overfitting issues? Like,
Overfitting, yes. I mean, well, I mean, there's always the problem of overfitting. But in general, I don't think this is a big problem for overfitting. I mean, the more data you have, because also there is some correlation with that. I mean, this is not like solving a problem of 2 + x is equal to 4. It's not a problem like that, right? So there is some dependency on the variables here. So there is a correlation between rain and flooding. So one variable might be correlated to multiple variables. So, I mean, if you have more variables, I don't think that's a big problem for machine learning. On the contrary, I think machine learning will give you a better results if you have a, if you overfit a problem. But personally, I don't think this is a problem for machine learning. The problem will be if it is underfitting. If you don't have enough variables and you are trying to predict something, then you will have a problem. But here, overfitting is good, I think, in machine learning, in my opinion.
got it, thank you.
Okay, Shruti, go ahead.
Thank you for the talk, Dr. Leo. My question is there a way by which we can extract air to prevent geysers in CSS?
Yes. Hi. So that's exactly what we are trying to do. So we use manholes. Manholes basically are vertical shafts. And the idea is to release the air little by little. If you release the air drastically, like if you have a big shaft and the air is released suddenly, then you are going to have a geyser. The idea is to kind of reduce the amount of air that can be extracted. So if you control that amount, then you can prevent geysers. That's exactly what we are trying to do. We are trying to control how much air we should release, and then minimize geysers.
Yeah, thank you, Shruti.
Thank you.
Are there any other questions? Yeah, I have just one that just sort of popped into my mind here. I think I read recently that the diameter of the shaft, or maybe the diameter of the manhole itself, has a effect in controlling geysers. Is that something that could be factored into the design of combined sewers?
Yes. So there are multiple variables, and yeah, exactly. So if you have a big manhole, you might have two problems. First, if the manhole diameter is too small, the amount of rain coming from the amount of water coming from the rain might not be, might be too large to pass the flow to the manhole or to the shaft. So that's one issue. So in that case, you might produce flooding upstream of the manhole. That's actually what happened in Chicago. In Chicago, the diameter of the manhole was too small. So a lot of the water would basically flood the area surrounding the pumping station. So in that case, we asked to increase the diameter of the shaft. So that's one issue. Now, if it is too big, and you are dumping the water in the drop shaft, then that also might be a problem because you are dumping the water at a single location, and that might create to the entrapment of air. So if you add water only at a few locations, those might be kind of places to trap air. So the idea, the best would be to kind of distribute the inlet of water through multiple locations. So in that case, you are trying to, before the system fills, you are trying to kind of making sure that the air is released before it's pressurized. So that would be the best. So kind of what we call distributed filling of the system. That is the best in terms of filling the combined sewer system.
I see. Well, Dr. Leon, I think we're going to wrap up here. I think our students will be happy to have an extra 20 minutes to work on their research. Thank you again, everybody, for attending. Dr. Leon, just stay on the line. Okay, you can
Thank you so
sign off
much,
now,
everyone.
everybody.
Thank you, everyone. Thank you so much.